Hello YouTube, welcome to this video, and today we are going to be looking at escape velocity with regards to gravitational fields. Alright, I'm going to be first showing you a little brief explanation and then we'll tackle a couple of problems. Let's get started. Here we have the equation for escape velocity, where v escape is equal to the square root of 2gm over r. The capital G is the gravitational constant. The capital M is the mass of the body, and the r is the radius of the body. The reason the M is capitalized is because usually you're going to be plugging in a very large mass in there. Hence why the capitalization shows the magnitude of the mass. Well, that doesn't always have to be the case. For instance, you can plug in the mass of a nucleus and you're trying to calculate the escape velocity of an electron. Alright, anyway, let's go with an example where we have a planet, and I'll just color that in, and we have a satellite orbiting this planet. And I'll draw the satellite in white. And I'll give it a few solar panels. There we go. The escape velocity essentially gives this body enough energy for it to escape the gravitational field of influence or sphere of influence of the planet. When it has reached the escape velocity, the satellite leaves its orbit and continues on this path that is signified by the white line. And then it will just continue on in space until it reaches another body that has a gravitational sphere of influence, and the satellite gets captured by that. Alright, now let's take a look at these problems. What is the escape velocity of Earth? That should be easy now. Just a matter of plugging in things. So v escape is equal to square root of 2 times capital G, which is a gravitational constant and has a value of 6.67 times 10 to the negative 11 Newton meters squared over kilogram squared, and that is multiplied by the kilogram mass, or the mass of Earth, which is 5.98 times 10 to the 24 kg. That's very massive. And this is all going to be divided by the radius of Earth, which is 6.38 times 10 to the 6 meters. Okay, and the answer that we should get is equal to 11,181.966 meters a second, and that is approximately equal to 11.2 kilometers a second. When looking at orbital speeds and escape velocities, we usually look at it in kilometers a second rather than meters a second, since the meters a second values are enormously large. Alright, now we've got that question down packed, let's look at the next one. So in this question, we'll have to do a little bit of rearranging with the equation. So we have v escape is equal to square root of 2gm over r. We'll have to square root both sides to get rid of the square root. We have to square both sides to get rid of the square root. So v escape squared is equal to 2gm over r. We have to solve for the radius, right? Since it's in a cross multiplication configuration, we can just swap the r and the v escape squared. R is equal to 2gm over v escape squared. Now we can plug in the respective values. So 2 times g is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, multiplied by the mass of Earth, or sorry, the mass that is given here, 6 times 10 to the 25 kilograms. And that is all divided by 1.2 times 10 to the 4 meters a second squared. Whoops. Command Z. Let me just make the R positioned a little bit neater. R right in the center there. R is equal to, okay. And then R approximately equals 5 point, that's going to be 5.6 times 10 to the 7 meters. All right, so there we are. We have been able to solve the escape velocity of Earth, and we've been able to rearrange the v-escape formula such that we can solve for radius. I hope you found this video informative. If you have any questions, please don't hesitate to drop them in the comments below. And also, stay tuned for a dedicated video that I'm going to be making about escape velocity. Well, thank you for watching. See you next time.